Hello. Yeah, welcome everyone to this second general audience talk associated with the workshop Isogeny-based crypto, which still will run for another 6 weeks here at OIST. And for this talk, we have Péter Kutas, who's associated with the Eötvös Loránd University and the University of Birmingham. Another great man who needs no introduction and has proven several important results in the field of isogeny-based crypto, a subset of post-quantum crypto, which he will talk about today. Please take it away.
Can you hear me well?
Yeah.
If I get too, I'm probably too loud even without the mic. So indeed, in the talk title, I will propose we can just do this. Okay, so today's talk will be about post-quantum crypto and its standardization efforts, and I kind of don't want to assume any knowledge about cryptography because I don't know who was interested in the talk from OIST, so I will start from the very beginning, which basically means that maybe I should stand here. So whenever you're communicating on the internet or in any shape or form in an online fashion, you kind of want to communicate in a way that is kind of privacy preserving. Your communication is not seen by the other party. And cryptography kind of boils down to two very different disciplines based on the fact that the two parties have the same secret key or a different secret key. And indeed, cryptography where the two parties have the same key is called symmetric key cryptography. And that is actually very fast, is also relatively secure, has been around for ages. So that's really the branch of cryptography that originates from 2,500 years ago. But it's also very inflexible, right? So you kind of, the two parties have to come up with this shared key that they both of them use. And traditionally, this was done in the age of Julius Caesar or Mary a little bit later, is that they came to a place and they agreed on a method and they agreed on a key. But imagine that in the new world where we use the internet every day, this is not really a feasible scenario. If you want to communicate with a person or access a web page, that you go to a cafe in a very secret spot and agree on a secret key. So the way this now works is you use public key cryptography, where the two parties have a different secrets to come up with a shared key, and then usually you continue to use this shared key in symmetric key protocols. That's one big branch of how communication works. The other one, which often gets forgotten. So I mean, everyone has heard about encryption. I want to encrypt what I want to send. But the other part, which is probably not so known to cryptographers, that you also have to authenticate yourself. So you receive a message saying, Japanese government, please send 55 million yen to this bank account because you owe this amount of money to the Japanese government, and you want to make sure that that email comes from the Japanese government and not Joe from Starbucks who wants 55 million yen. So you kind of have to prove that you're really the person you're claiming to be. And these are really the two cornerstones of many, many protocols, but there are a lot of other protocols as well, which we also use. So for example, a lot of more advanced notions come up in blockchain applications or in messenger applications like Signal or WhatsApp. So there's really a large variety of things you want to establish in a privacy-preserving way. And this you can all establish using public key crypto, which is a very inflexible way of doing things. Of course, the caveat of public key crypto is that it inherently relies on something called hardness assumptions. So you don't have information theoretic security that this is secure because of information theoretic reasons. It's secure because there is some problem, some computational problem that seems to be intractable. Right. But, I wish this worked, but okay. So what are these problems that no one can really solve? So classically, this boils down to two types of problems. One of them is someone that probably everyone has heard about in high school or whenever, that if you get a really, really big integer, that's very hard to factor into its prime factors. And the other one is the discrete logarithm problem. So that was kind of the gist of last week's talks by Stephen, which is you're given a group G with the generator G, and another element in the group H, and you want to write that other element as a power of G. And these problems have been around for a very long time. I mean, factoring has been studied in again by the Greeks and then Euler and whatever, again 2,000 years. Discrete logarithm not so much, but that has also been around for the last 50, 60 years. And people have really scrutinized these problems. They know how to, what are the weak instances, what are the hard ones. And this is what our current security infrastructure relies on. So now the main problem is, which I think OIST has some groups in that area, is that these problems have been studied in the classical setting, and in the 1990s it was discovered that if you allow quantum computers and quantum algorithms, then these problems are no longer hard. So you have polynomial time algorithms both for factoring and both for discrete logarithms. They all kind of rely on this one uber quantum problem, which is this hidden subgroup problem. And they all boil down to this quantum Fourier transform that is really what makes these problems easy quantumly, but what makes them easy for quantum algorithms. So quantum computers are not here yet. I had previously some slides about whatever, but I mean, probably here there are better experts at quantum technology than I am, so I don't want to claim that I'm an expert on these, but there has been some emerging progress in that area. So we need cryptographic protocols, which are still secure if an adversary has a quantum computer. And but we really want to instantiate these protocols on actual classical computers. So we don't want to, this was also emphasized in Stephen's lectures last week, that we don't want to change our current hardware infrastructure. We want to use just replacements. So basically what we have to change is not rely on factoring or discrete logarithms, which seems like not such a big deal at first, because there are so many algorithmic problems that are hard. And it's also kind of what I want to also emphasize here about the fact that we're only using classical computers is this is a branch of quantum technology where you only assume that the enemy, that your adversary, has a quantum computer. So even if somehow quantum computers never materialize, there is always a risk that they might, unless you might be able to prove that they can't be materialized, which is probably not really possible. So this is a threat you have to take seriously. Because in cryptography, we want to make sure, and we even go beyond sure in certain cases, that our systems don't get cracked. So even if quantum computers never materialize, this is an important research subject. So what are these problems that we switch from factoring and discrete log? So there is several of them, and I will, here is a quick list, which I will go into later, so there's no reason to tell all of them, but there are several problems that you can choose here. Okay, So in the talk title, I mentioned something about standardization. And this is, again, something that happens in the wild, and that is happens so much that people came up with this expression, which is called never roll your own crypto, which basically means you should not invent your own crypto protocols and then use it in real world products. Again, because you don't want to get hacked, right? So the way cryptography works is it starts from the theory. It starts with a large research community researching a bunch of protocols, and then time passes, 10 years, 20 years, they don't get broken. Maybe I'm exaggerating a little bit. And then once enough people have looked at it, then you deem these things secure, and then you start deploying them in practice. But this has to be scrutinized by a large amount of researchers to get some sort of assurance. So another thing which is not quite the same as never roll your own crypto, but it's also very dangerous to do your own implementations of cryptographic protocols, because there is a lot of pitfalls you can do. A very good example was, I think Toshiba had a printer which implemented RSA, which is based on factoring. So in RSA, you want to have a secret key, which is the product of two large primes. And you kind of want the two primes to be of the same size. And they said, oh, we make them exactly the same size. And they chose the nth prime and the n+1 prime. Because those are really so much of the same size, they're actually neighboring primes. You can think about yourself how to break the scheme. It's very easy to break. And that was something deployed in practice. So really, you should not invent your own crypto protocols. It should be studied by a large community. And even then, you should kind of use implementations that have also been verified and are ready to use and also done by experts. Okay, so how does this work? So usually the way this works is that there are large bodies that launch competitions for standardization, which standardization can mean a lot of things. A lot of things in the world get standardized by a lot of standardization bodies. So I named three here, but the most important one that we'll be talking about today is NIST, which is the National Institute of Standards and Technology, and is a branch of US government. And they were the first to say, okay, so quantum technology is advancing pretty fast. Maybe we should act. So just to note that this is 2017. So Shor's algorithm came out in 1994. So back then, people knew that this is an actual threat in some sense, because there are polynomial time quantum algorithms for these problems, but no one really took it seriously because quantum technology was really nowhere. And that was kind of the point in time where they decided that quantum technology is emerging enough that we should now really act. And they launched a competition to standardize, again, two different things. Key establishment, which is basically, again, what I meant, that you have two parties have their own keys and you want to get the shared key. And digital signatures, which is a way of authentication. So only restrict to these two things, but these cover many, many applications. Okay, so how did this happen? So initially, there were 69 submissions. I also have a more detailed one later if someone has a question of like how many were in each round. But initially, there were 69 submissions. I think they released the first batch around December in Christmas time. And this was, it kind of shows that scrutiny is important. So some were immediately broken. I think the first one was broken 3 hours after things became public. So Lawrence Punny, who will be at this workshop in 2 weeks. So he had, I guess that was his Christmas holidays. He was a starting PhD student, and in his Christmas holidays, he broke some of the submissions. So, but then breaking them became progressively harder. So eventually there were 3 rounds. think round 2 was announced in the summer of 2020. And then in 2022 July, they made the final announcement, or almost final announcement, where they selected certain schemes to be standardized. A small anecdote there, which is not on the slides, is that so the announcement was supposed to happen much sooner, or much sooner meaning around March-ish, I guess. But then it was derailed by patent issues. So that's something, again, if you're not in cryptography, and they always ask me of like, oh, if you're studying cryptographic systems, how can you make money off them? Maybe you should patent them. And that's really a big no-no for cryptography and standards, because exactly this is the thing that can happen. So someone had a patent that looked very much like this, one of the selected schemes, but only to the completely untrained eye. I think only to the lawyers, not to any of the experts. So kind of like a whale looks like a cat. They're most mammals, and that was enough for the lawyers to drag this on for 5 months, and then someone had to be bought out. So there was a lot of drama behind the scenes, but eventually in July they selected one key establishment called Kyber. And then and 3 digital signatures, dilithium. That's another thing if you're not from cryptography. So cryptographers, they come up with funny names for their schemes, especially for their actual submissions. I think Kyber is the material of lightsabers from Star Wars. There was also Saber, which was more direct, but that didn't make it. Dilithium, I think, is also Star Wars or Star Trek, I'm not sure. And then Falcon and Sphinx Plus. And then they said, we move 4 key establishment to an imaginary, or not an imaginary, an actual 4th round. So this was like a bonus round that they didn't have, that we only selected 1 key establishment. And there is always this argument with standardization that you don't want to put all your eggs in a basket. So there is no provable guarantee that any of these things are secure, other than good enough evidence and enough years of scrutiny. So you want to make sure that you don't bet on one horse. You kind of want to bet on as much as possible. So they said, okay, there is 4 more schemes that look promising enough. Let's move them on to this extra round. And then a disaster struck actually very quickly. So they made this announcement, and one of the schemes, one of the 4, was completely broken less than a month after the announcement. And one other thing which I didn't mention that also prolonged the decision, I'm sure, is that one of the top candidates of the digital signature schemes was broken in February. So probably that also prolonged the decision, because I'm sure they wanted to standardize that, but then it was completely broken. And they had to rethink their position a little bit. So this kind of shows that this is a very fragile process, and it's very, very necessary, because these are schemes that have been around even for years. So the one that was broken in February was around for 17 years, the other one for 11 years. So this is a lot of years, a lot of researchers looking at them, but you really need these processes to make sure, or at least minimize the probability that you end up using something in practice that is insecure. Yes. So this is when they made the announcement. So in 2022 July, they said, okay, we are standardizing these schemes. But this was a decision, right? So it was not something that you could immediately use in practice. So it took more than 2 years to actually draft the standards. So the standards are really the actual document that really tell you how to use these schemes, what parameter sets to use, how to implement it in a secure way. which might still not be enough for your application. They don't contain any implementation. So at some point, you kind of have to rely on other people to actually implement it. And they renamed things because clearly this like Star Wars stuff doesn't look so nice. So they had like more generic names, like Kyber became MLChem, Dilithium became MLDSA, Sphinx Plus became SLHDSA. And one of the selected ones, didn't even make it. So there is no current standard for Falcon, which will be called FNDSA, but the standards are not available because there is some complication with Falcon that makes it actually quite difficult to implement in practice and even to write a standard. And then in 2025 March, they finally, so out of the 4 candidates that moved to the 4th round, so 1 was out, but 3 still remained. And one of them, called HQC, was selected this March, but again, just selected. So there is no standard for that yet available. And now the question is, are we done with standardizing post-quantum cryptography, or is post-quantum cryptography a solved problem? I'm putting this explicitly because I know of someone who applied, I think exactly around the time of 2023 to a postdoctoral position in Switzerland, and then it was in the topic of post-quantum crypto, and he received a review from someone that this is not a research topic anymore. Post-quantum cryptography is done. Why would I give a research money to someone who is working on a project that is already finished? So it's far from finished, and I will try to give some justification for it. The one thing that is very important is even if you have standards, you have to integrate them into protocols, which is sometimes easy, sometimes not so easy, and some of them are already integrated. So MLChem, which is this key establishment, is integrated into the newest version of TLS, which is basically, if you also, this is exactly what Stephen showed last week as well. If you look at your browser and you click on this lock button, I probably don't want to do it right now because I'm not sure I will get this back. You can see what protocol is used to access a website, or if you look at in your Gmail and you say, oh, this is encrypted using TLS. So it's really the basic protocol for communication between many things. Also, if you do any credit card transaction, that's the protocol that is being used. And so this is produced by a company called Cloudflare, and they track how many people are using already the version with MLChem in it, and now it's like 50% of actual usages already use MLChem. So this is something that is not science fiction anymore. You might be already using it whenever you're surfing on the internet or writing emails. And another application that also made the news was using end-to-end messenger protocols. So usually cryptographers say Signal, but if you're not a cryptographer, you might have never heard of Signal. But then hopefully you have heard of WhatsApp or I think it's called I don't have Apple products, so I don't know, but I think it's called iMessage or something like that. One very important thing, which is also a really big misinformation, is that these protocols, which are all based on Signal's protocol, they just took it and slightly modified it, except for Telegram, but that apparently doesn't make any sense. So it has a lot of features that protect your privacy. Those features are not protected against quantum computers. The only thing they shielded against using integrating MLChem is a type of attacks which I should have mentioned earlier. It's called harvest now, decrypt later attacks, which basically okay, now we don't have quantum computers, but we do a lot of encrypted communication. So you see a lot of encrypted plain text, and someone can collect all those plain texts and then wait for the quantum computer quantum computer arrives, you decrypt all of those plain text, and sometimes you get useful information out of it, right? Not. If you text your friend, look, let's meet at the restaurant, that might not be useful in 10 years, but if it's military secrets, and I mean, now military secrets are being passed along signal. If you've ever read the US news, maybe that's actually a good thing that they are protected against harvest now decrypt later attacks. Okay, so ML-Chem is really already being used in practice, but if you listen closely, I was not talking about signatures. So signatures, you say, oh, this was a success for signatures because they only standardized 1 chem and then 3 signatures. But actually, the reason they standardized 3 is because none of them were very good. They're bad in different reasons. So current infrastructure, especially elliptic curve signatures, they're very small, they're very fast, and we really know how to implement them very nicely. So none of that is true for all of the 3 candidates. So dilithium is very big. What does that mean? So like an elliptic curve signature is, let's say, 64 bytes. A dilithium signature is 8 kilobytes. So if you have an application where you store signatures, let's say blockchain or even TLS, where you store certificates, it requires more than 1,000 times the storage, which you don't want, right? Because you care about the planets, especially with blockchain. And Falcon is a little bit slow and also impossible to implement. There are no standards. And then SLHDSA is kind of like is an apocalyptic solution that is very secure but very inefficient. It's good for software updates apparently, but not to replace in TLS. So they kind of made this conclusion that okay, this is not good. Luckily, signatures, they don't have harvest now decrypt later attacks, so you don't have to migrate its signatures. You can take your time and try to find better ones. So what this said, okay, let's launch a new competition. Now chems are out of the picture. We just focus on signatures. And what we want is signatures that have been around for a long time. Again, not put all of our baskets, so I didn't mention, but all those signatures that were chosen, they're all based on lattices, one particular branch of post-quantum cryptography. So maybe let's diversify our portfolio. Let's do something that is vastly different, but has been around for a long time, and then we can use it. Maybe we can't use it in all applications, but we can use this in this application, that in another application. So that was the expectation. Of course, the reality was vastly different. So when people submitted stuff to this new competition, there were obviously lattice-based submissions, and most submissions have been around 2 or 3 years. But that's life. That's what we have. As a mathematician like myself, I find this competition very exciting because mathematically it's much more interesting than the first one. So the diverse areas of mathematics that are involved is much more interesting. And I will try to shed a little bit of light on all of them. I mean, it's I can't get into all of them because of time constraints. So very briefly, what I will do in the rest of the lecture is I will try to go through, I mentioned these terms of like lattices, codes, or whatever, but I didn't define any of them. I will try to give a little bit of intuition about all of them and their pros and cons. And then I will cherry pick 2 schemes that I actually want to explain how they work. Okay, so lattices, so what's a lattice? A lattice, this is a good time to draw a picture. So a lattice is the Z-span of, so it's the free abelian group generated by vectors in R to the n. So this is a 2-dimensional lattice generated by this vector and that vector. And they pop up in many applications in mathematics. They're very natural objects because they are abelian groups. So you have only one operation, you can add them, and they are embedded in R to the n, so they have some geometry. And that makes them simple enough that they pop up everywhere, and but interesting enough that you can say interesting results about them. And the natural, I mean, there are several hard algorithmic problems, but the most natural one is that you're given a lattice with a basis, and you want to find the short vector in this lattice. Of course, I can only draw in 2 dimensions, and in 2 dimensions, this problem is actually very easy and known since Lagrange and Gauss, and I don't know, probably other people. But what lattice-based cryptographers care about is more like 1,000 dimensions. I can't draw that. I don't think I can even draw 3. So, but indeed, it's in very high dimensions. This is a known hard problem. And based on the hardness of this problem, you can build a lot of schemes. I will mention one during this talk. They are usually very fast, usually even competitive with classical ECC and RSA. They're also very flexible, which comes from the flexibility of one particular assumption, which I will mention later on. So you can build almost anything you could build previously with elliptic curves or factoring. But usually the downfall is that they're a little bit bigger, because you have to work in really high dimensions, and these like 1,000 dimensions are really the thing that will make things a little bit problematic. And if you think that's not a problem, so indeed one application where this can be a problem is for signatures when you want to store stuff, or let's say cryptography is also used in resource constrained devices. So let's say your ID card has some cryptography in it usually, or passports, and it has a small chip in it, and that has size limitations. So that's their main downfall. So isogenies is what this workshop is about. So here the hard problem is, so it can be considered as a branch of elliptic curve cryptography, whatever elliptic curves are. These are kind of curves with some very nice structure. And isogenies are certain kinds of maps between them. And finding these certain kind of maps is hard. The good point is that they're usually very compact. So they're the opposite to lattices. They're usually very small. So you can design signature schemes which have public keys and signatures just as small as elliptic curve based schemes. They're also quite flexible. You can do a lot of stuff with them. But they're much slower because of the fact that their maths is very complex. And this is what this semester is about, of like looking at making these schemes faster, breaking certain schemes, and looking at their mathematics, which is by far the most complex. Although maybe that's a biased opinion, but it's definitely very complex and very interesting, and a very good topic for someone who is coming from maths. So then multivariate, that will come up. I will give an explicit example for this. I will probably not talk about this too much because I will have an explicit example here, but the hard problem here is a very natural one. So the hard problem is you have a system of equations, and your system of equations is quadratic, and you want to solve it over a finite field. And basically, if you think about it, like any Boolean circuit, you can kind of represent this as equations. So it seems that this is as natural a problem as it gets. Of course, to find systems which are usable for cryptography is a much more difficult issue, and they have a terrible track record. So there is usually always like I come up with a scheme and then it gets broken. The one that got broken at the end of the first NIST competition, Rainbow, that was also a multivariate scheme. So it's a very, very challenging area to build secure schemes, but they're usually very good for signatures. Not anymore for encryption or key exchange, but they're good for signatures. They have generically they have very big public keys and small signatures, and fast signing, and it's very easy to verify signatures. So they're really good candidates modulo the issue that they have very big public keys. But there might be some counter things which are so bad. So code-based is based on So error correcting codes, they pop up as well in a lot of practical applications. So this is the area of error correcting codes is that you send a message through an uncertain channel, but the channel might be noisy, so some of the bits might flip. And you want to send some extra redundancy to be able to retrieve the original message. And this is the technology used in QR codes or whenever you're sending a text message or in many different areas. But the codes used in practice, they have this feature that they are decodable. So indeed, if you send a message with some redundancy, there is some noise that happens. You are able to retrieve the original code. But if you pick a random code, this problem is a hard problem. So this is actually a big problem with classes on error correcting codes. So if in a maths program you take a class on error correcting codes, the ones I've ever attended, they never talk to you about decoding algorithms. They only talk to you about, oh, this code can correct this many errors and whatnot. They never talk about decoding, and that's not really good for an engineer. You probably would not be happy with your QR code if you scan it and it says, okay, this message is decodable, but good luck. But in any case, in general, this is hard, and you can build both encryption schemes and signatures from it. So one of them, the McAlex crypto system, is a very old one that has not still been broken, although there has been immense progress now against it. So this kind of shows that maybe after 50 years there is still something to say about it. But HQC that I mentioned before, that's a code-based one, so they're really good for encryption. Not so much for signatures. I mean, there are some signatures in the NIST competition. I would not bet too much money that any of them would make it in the end, but they are there. Finally, there are two more branches which probably I will not talk too much about. So hash-based and multi-party computation-based schemes, these are really the ones which are the most secure. They rely on very conservative assumptions, but they have very limited applicabilities. I mean, maybe not the MPC-based are getting better and better, but yeah, they are not so. Yeah, I will not say too much about them. As a mathematician, I'm not so interested in those because they're not so interesting to me. But very good for conservative applications. So I put some interesting slides here. So if you really want to see a picture of all possible candidates and how they compare to each other and how they compare to RSA and ECC, so a very good blog post from Cloudflare from maybe 2 years ago, and then there is a slightly older one. I think that's from the NIST PQC seminars. And then the last one is this PQ sort TII. So that's an institute in Abu Dhabi, and they set up a very nice website. Like I think it's mostly not just signatures. I think it really all of them, and you can really play around with it of like how they compare to each other. So you can really see this picture. But basically, the picture more or less is that they are more like incomparable a little bit. So some branches are good at this, some branches are good at that. There doesn't seem to be like a universal solution like ECC. Okay, so I wanted to give at least a tiny amount of actual schemes and how they work. But before I do that, this will be a lattice-based candidate. But I will want to explain a very important problem in post-quantum cryptography called learning with errors. So the way I like to introduce it, I didn't come up with it myself, but I took it from someone and I like it, is you start with a game. And your game is very simple. There is a person who has a secret vector. And the goal of the game is that you want to find the secret vector of that person. And the queries you can make to this person is that you submit your own vector, and that person gives you the scalar product of their secret vector with your vector. And then you can make queries like that, and then you want to get the secret vector from them. So if you think about this problem for 55 seconds, I mean, sorry, that's a little bit. That's a little bit. It was a little bit of an arrogant remark. Sorry about that. But anyway, if you write down a very explicit example, maybe I should do that actually. So if you think about, let's say their vector is something like x and y, and then you ask about the scalar product with this vector with like 1, 0. And what's the scalar product of that? That's just going to be x. And then you ask about the scalar product with 0 and 1. That's just going to be y. And then you have the secret vector. So clearly, we should not base cryptography on that problem. But that problem would be called learning without errors, or just learning. So the error part is the important part. So learning with errors, you submit your vector, but you don't get an exact answer. You get the scalar product plus some small error, right? So for example, there I would not get x, but x plus epsilon. And I would not get y, I would get y plus. And now imagine that you have a much longer vector. And even if the error is kind of like plus minus 1, you can't go through all the possibilities to get the to get rid of the error naively. Of course, there are much better algorithms to do it, but essentially this will lead to, you can kind of model it as some sort of lattice problem, essentially, not a short vector one, but a close vector one, which is, so in a short vector problem, you want to find the short vector. In a close vector problem or closest vector problem, you're given a vector anywhere in R to the n, and you want to find the lattice point that is closest to you. Again, this is a very misleading picture in dimension 2 and with the lattice that is this nice. So again, if you're in 1,000 dimensions, your options are much more difficult.
Peter?
Yeah.
Might be worth pointing out this is very much mod P.
Oh yes, yes, indeed. Yeah, you kind of work modulo a large, middle large modulus.
Otherwise, least squares solves this problem. Otherwise, this problem could be solved using least squares.
Okay. Yeah, so indeed you reduce modulo some modulus q. But I will give you an explicit example of how this comes up in an encryption scheme. I decided to go back to the original one, which is due to Regev, who kind of discovered this learning with errors problem when he wanted to do a reduction between two problems, and in the middle this problem popped up. But then he decided to make it into an encryption scheme. This is I will only explain the simplest version, and that can be tuned to make to be better. But in the simplest version, I only want to encrypt a single bit. Right? I only want to encrypt 0 or 1. And I have the following data. So I have a matrix A, which is not a square matrix. So that will be public. X, which will be a short vector, will be private. AX will be also public. I will call that U. So that's why I mean that A is not a square matrix. So from knowing AX and A, that doesn't give you X, really. And now I will probably, that was the point, one of the parts where I really wanted to write as well. Is there some sort of, I mean, I'm also full of chalk anyway, so I can probably just do this.
Behind the board, I think.
Yeah.
Yes. So, so what you will do is you will compute, first you will compute kind of like a vector, which I call B1, which will be S times A plus E1. So S is, so now Bob is the one who wants to encrypt something. So he only knows the public key, but doesn't know the secret key. And then chooses some random vector S and computes S times A plus E1, where E is a small error vector. And then also computes, this will be a number. So this will be the scalar product of S and the vector U, but I'll actually just write it S times U. I'm a little bit sloppy. I should have said the transpose here or like that to make it more precise, but yeah, sorry about that. You had a small error, which is again a small number here, and here comes the funny part. So far you have not used the secret bit, the bit that you want to encrypt at all.
Is it? There's a brush like just under the.
Where? Yeah, that comes from the fact that the group has been using the other side of the board. But I can't show that because they have proven the Riemann hypothesis on the other side. So far I have not used the secret. And this comes and this is indeed this modulus that Stephen mentioned, is that you multiply the secret bit by q/2, which you round to the nearest integer. And now, so this is how you encrypt. How do you decrypt? So the trick is that you take the scalar product with this with your secret vector x. So if you do that, you kind of get this S transpose x plus x. And now, if you remember that U was actually A times X, you see that these two are the same. So let's get rid of that. Let's subtract that from that. You get E2 plus somehow the scalar product of E1 and X. Sorry, that's minus plus C times q/2, and then you round it. And now you look at this quantity, and this will be very imprecise, but hopefully very will show you how this really works. So this is an error vector. Error is small. This is the scalar product of two small vectors, so also small. Now this, if C is 0, and will be small. So the good way to represent it is you write residues modulo Q on a circle, and when C is 0, you get the quantity which is small. So it will sit somewhere here. If C is 1, you add a q/2 to it, so it will land somewhere there. So the very imprecise way is that you compute this quantity. If it's small, then you've encrypted 0. If it's big, you encrypted 1. You can make it slightly more precise by saying, I don't know, is it on the bottom or is it on the top? On the bottom, it's 1, 0. So this was Regev's original key exchange, slightly reformulated, so you might have seen it in a slightly different fashion. So this is an equivalent formulation by Chris Pikert, and probably also Gentry and Vaikuntanathan from 2008. But it's basically the same scheme. Of course, if you think about it, it's incredibly inefficient, right? Because you went through all this trouble to just encrypt a single bit. And everything has to be very, very big. And now to encrypt like a bit sequence, you have to iterate this procedure I don't know how many times. But this is where things start out. You come up with a scheme, which is probably secure, and then you make it better. And through time, it has evolved a lot, mainly by. So the main difficulty here is that. So here I have a vector, and here I have. Just a scalar, because if you have two vectors, the only thing you can do is you can take their scalar product, and then you move from a vector to a number. So one of the ideas of the major groundbreaking ideas is to use special kind of vectors, which will come from polynomials modulo certain moduluses, where you can multiply vectors. So any matrix will turn into a vector, and any scalar product will turn into an actual product. and then you can basically repeat the exact same scheme for a C, which is not a bit, but a sequence of bits. And so these come from lattices which have a ring structure. So this version is called ring LWE. And then there is module LWE, which kind of lies in the middle. Alternatively, you can also think about the fact that in the original version, A is kind of like a random matrix. In ring LWE, it's kind of like a circulant matrix. And then module LWE is like blockwise a circular matrix. But throughout this 17-year history of this encryption scheme, this has become very, very efficient and also somewhat compact. And this is something we already use in the form of MLChem. So this is the chem I wanted to mention. And I took one digital signature scheme, which is in the second competition, that I want to explain, but I have no idea how much people know about digital signatures. So I will kind of first tell you what they are, what you expect from their security, and how you can build them in a generic way. So in a digital signature scheme, you want to prove who you really are. So the way that is done is that a signer has a public key and a secret key, and the verifier can only use the public key to verify a signature. So a signing process is that the signer produces, so we'll send a message. So the message will be known to the receiver. Send 55 million euros to this bank account. Or it was yens. And also produces a signature using the secret key, which is just some bit string that the verifier has. And then the verifier, using the signature and the public key, should decide whether he accepts that the signature is valid or doesn't. So it's basically a way of like linking your signature to your public key in a secure way. So, but the security here is a little bit harder to model, or a little bit, you have to think a little bit more probably than for encryption. So again, I will be a very informal description of how security works. So of course, the generic goal is that you don't want anyone to be able to forge a signature, even for a message that they can choose. Right? So you should not be able to produce any message and signature pair that the verifier would accept. But that's not quite enough. So you also have to tell what tools you give to an adversary. So what can they do? What they can do is they can observe as many valid message signature pairs as they like, of course, within reason, so polynomially many in the input parameter. And even using that, they should not be able to forge a signature. Very brief thing, and this is the type of security. So basically, that's trying to model that whenever you sign certain message, you're not leaking any information about your secret key. So there are basically two generic ways of building signature schemes. I will explain one, which is so they can be quite hard to build, but luckily these guiding principles make it a lot easier to build signature schemes. And so this framework is called hash and sign, or full domain hash signatures. So assume now that you have a function that you can evaluate very efficiently, but it's surjective, but it's hard to invert. You can think of discrete log, for example. I can evaluate given g and given x, I can compute g to the x, but given g to the x, I can't compute x. But there are many other functions that are like that. But it's very important that it has to be surjective. And that would not be enough, or actually would be enough, but that's a different thing. So you also assume that the person who is going to be the signer has some sort of piece of extra information. And if you have access to that piece of extra information, then you can invert this function for any value in y. When I mean invert, it's a surjective function, so I can find some pre-image. There will likely be exponentially many pre-images. Okay, and then the generic way this works. So once you have access to such a function, you can build a signature scheme in the following way. So the public key is some sort of description of this map. And then the secret key is this trapdoor information, this extra piece of information which helps you invert. And then what you do is you take the message together with some small randomness, you hash onto Y. So that's also very important, that you should be able to have a hash function that hashes your message onto the image of the function. And then the signature is just a pre-image of the hash of the message. And then you can verify very easily. You just evaluate your function on this pre-image and check if that's really the hash. And so it's a very generic framework. It's not always very easy to prove security, but because it's very hard. Sometimes it's hard to prove that this Z value doesn't leak any information about the secret. And there are certain attacks, actually on a very nice lattice attack on a class of lattice-based signatures using that, where it does leak some information and you can actually exploit that. Okay, so now we will try to construct this function, this trapdoor one-way function, which is surjective. And then we will not speak about signature schemes anymore, because then we just use this generic framework. So how can you construct that from systems of equations? So basically, the idea is the following. Of course, if you take any random system, that's very hard to solve. So no one can solve it. So you really need to find a system that with some information you can solve. And the generic principle, and this is where you will see that why MQ signatures are a little bit clunky, is that I find my favorite system that I can solve, actually anyone could solve very easily. Then I take some secret transformations, and using these secret transformations, I build a new scheme that looks random. And then I do this hash and send principle. I hash onto so basically the way it works is a system of equation has a left and the right hand side, and I design systems where I can solve the equation whatever the right hand side is, and then I only transform the left hand side. So the way this inverting really works is I get the right hand side, I transform my random looking system using my secret transformations into the easy system. I solve the easy system and transform it back. And usually that's the really big problem, because you have to come up with a system that when you do these transformations, you can't find these transformations to come back to the original system. So I will give you one example that really stood the test of time. So it's called oil and vinegar. It's on the board as well, but I think it's better to write here. It's on the slide. So again, now my goal is to find systems which are easily solvable, and then I will just transform them using my transformations. And my systems, so every equation will be homogeneous and quadratic. In variables xi, but I will split my variables into two. I will have variables from 1 to O, which is for oil, and I will have variables from O plus 1 to O plus V, which are called vinegar variables. The name comes from the fact that oil and vinegar apparently don't mix. And so every equation will look like some sort of quadratic polynomial in these. But I will only take polynomials. So generically, there are monomials between any two, right? A generic system would look like something like xi, xj for all ij. So my system will not look like that. So if you take this big divide between the two of them, there are three types of monomials. You can take two oil variables. You can take two vinegar variables, and you can do mix and match. So my system will have two vinegar. We'll have vinegar. We'll have oil and vinegar, but no oil. So how can I solve such a system? So this is one equation. I have many of these equations. Actually, I will have exactly all of these equations. How can I solve such an equation? So what I will do is I will just plug in random vectors for the vinegar variables. This is over a finite field. I will just put something random here. And then how will my equations look like? So if I assign values to the vinegar variables, then all of my equations will be linear, right? Because there was no oil term. So the vinegar, I've assigned values. So this will be constant. And this will be linear because the oil are still there, but the vinegar have become explicit. So now I have a system of linear equations. And actually, I will have O equations and O variables. So likely that has a solution. If it doesn't, I will just choose a different choice of vinegar variables. Okay, and then what will happen is, of course, this is not the public key because anyone can solve such a system. So the exact terms of the system, so the exact coefficients, they are still secret. And I will also take a secret linear transformation from there, and that will be my public key. That will be the public description of my map, which is this like multivariate quadratic map. And I can just use my generic framework. So if you see that I've slightly changed from oil and vinegar to unbalanced oil and vinegar. So this was a construction by Péter. A year later, it was completely broken. So that's bad. But the reason being broken is that, I mean, the generic idea is that you take just as many oil variables as vinegar variables, because why would you take more? I mean, as it turns out, you should take more, because if you have the same number of oil variables as vinegar variables, there is a very simple attack you can run. There's an attack by Kipnis and Shamir. Essentially, you can reduce to a very classical problem in algorithmic algebra that you have a set of matrices, and you want to compute the common invariant subspace of these matrices. And that's very easy to solve. So what you do is you make this unbalanced. So you increase the number of equations by, so you have more vinegar variables now. So the safe choice is to take, or the safe choice right now is to take twice as many vinegar variables and as oil. Also, and this is now unbalanced oil and vinegar. Of course, the gigantic drawback of this scheme is that you have to have this gigantic scheme that you this gigantic sets of equations that you have to disclose to as a public key. So as a result, the public key is gigantic. It's like 66 kilobyte after 1 million optimizations. So now, recently there was a race of multivariate cryptographers to try to tweak it in a way that the public key goes down, and potentially the strongest one is the one called Mayo, which kind of creates this UOV system through a whipping up procedure. So the name kind of comes from the fact that if you take oil and vinegar and some emulsifier, then you kind of create Mayo. Again, as a cryptographer is being very funny. And then it really reduces the public key significantly to 1 kilobyte. But one very interesting thing is that, again, this UOV version, I think it's nicely explainable with coordinates. But then if you try to build on it, things can get really, really ugly. And one of the good examples is this rainbow scheme. which I mentioned was broken after 17 years. But the main reason was that no one really understood it for 17 years until finally Bart Boelens actually understood what was happening and was actually immediately broken to that. And the reason is that so he gave a version of this, which is kind of I call it a coordinate-free version or a geometric version. So I'm not going to I'm not going to write equations, but it will show something very interesting about the geometry of U of E. So the way you should think about it is you have a quadratic map from FQ to the N to FQ to the M, and that kind of defines a variety, right? You look at the vectors which are mapped to 0, and that gives you a variety. But this is not a generic variety. This generic variety has a large linear subspace, so large linear subvariety. So I mean, in the original version, I think it's whatever. It's a 2n-dimensional variety with an n-dimensional large linear subvariety. Now depends on how unbalanced you want to take it. The smaller the OIST space, but it's still a really, really big linear subvariety that's there. And the way the knowledge, the exact knowledge of this linear subvariety is going to be your trapdoor information. To be able to explain how signing works in this coordinate-free version, I will introduce this thing called the polar map. So whenever you have a quadratic map, you can kind of get a bilinear map from there by just taking qx plus y minus qx minus qy, and you call that pxy. And now, basically, when you're signing, you want to solve qx equals b. And the way you solve it is you pick a random vector r, whatever you like, and you look for the solution vector as r plus o. So r is now fixed to you, but o has to come from this large linear subvariety. And then let's look at this equation. So of course, so this is qx equals b. So qx is now qr plus o. So qr plus o is just qr plus qo plus now you have to correct with the polar map. But now the good thing about this OIST space, so it's a linear subvariety. So any element on the OIST space, qo is 0. So this will disappear, and only this will remain. Clearly, this is an o. That's not a 0. It's an o, and o is your flexibility. So r is a random actual choice. And now, if you look at this equation, this is linear, because this is a fixed choice that you made. And this is linear because it's bilinear, and one of them you put the fixed thing in there. And then you solve this linear system, and again, the things are designed that it's an O times O linear system. It's exactly the same thing I explained here. There is literally no difference. The difference is that this it's a different viewpoint. And if you come from algebraic geometry, it highlights a very interesting thing that you have a very specific type of variety that is not a generic variety at all, where you hope that it's hard to find points on it. So the question is it useful, or is it a lar pour lar, whatever? I want to say something obscene here, but let's not do that, of mathematicians. But as it turns out, it's actually very, very helpful. So first, basically, in this framework, Bart Boelens really defined what rainbow is, which I will not do here because of time constraints, but it really understood what this horrible million sets of equations really were. It was somehow two U of E instances stacked on top of each other. It really helped the design of Mayo. So the thing that I mentioned that is like U of E but has much smaller public keys really comes from this coordinate-free viewpoint. Then much newer research by Péter showed that you can use geometric properties of this variety to perform certain attacks. So there was an attack that was called the reconciliation attack, which is old attack on U of E. Basically, it somehow tries to find one element in the OIST space, and then the equations get nicer. You can completely rephrase this attack using singular points of this variety. Because if you have a large variety and you have a large linear subvariety, that will give you, so the Those will all be singular points there. A very new attack by Lars Strand that also improved on these attacks, on existing attacks, uses also very interesting tools from wedge products and exterior algebra methods called the wedge attacks. So basically, and I learned this from Wouter Kastik very recently, the way you should think about this attack is that if you have a variety, you can kind of parameterize its k-dimensional linear subvarieties. So it's a generalization of a Grassmannian, but in general it's called our Fano subvarieties or Fano varieties. And these are actually things you can actually compute. And what this attack does is that, I mean, if you think about U of E, you have an n-dimensional variety with an m-dimensional linear subvariety. So it would make sense to look at this m-dimensional Fano variety of the variety and to compute that. And as it turns out, if certain things align, you can compute this variety. The defining equations of this variety will almost all be linear. And you can solve them. That's, again, a very interesting, completely new approach. So, and then probably the future here is really to understand the algebraic geometry of these very special varieties and then move away from these generic Gröbner basis, brute force, whatever approaches. So I gave now two examples of actual schemes, so U of E and then encryption from learning with errors. But in this new signature competition, a lot of interesting computational problems pop up that are probably very interesting to mathematicians. So the first one is the code equivalence problem, where again, it's about error correcting codes. So error correcting codes can be seen as linear subspaces together with a metric, which is a discrete metric called the Hamming metric. And now you want to find, you have two codes, then you have two linear spaces equipped with the Hamming metric, and you want to find an isomorphism between them that respects the Hamming metric. That's a very popular one because you can build some new advanced schemes from there. The second one is somehow a classical problem, and but it's very unique. So what lattice-based cryptographers observed is so certain lattice algorithms that are used to build encryption or signature schemes perform much better if your lattice is very nice. So for example, finding the shortest vector in Z to the n is very easy because that's just drawing the grid, right? So that's very easy. But what if this lattice is somehow not given to me as your textbook or your exercise book, but it's rotated in very, very high dimensions? Is it easy to rotate it back? It also has some deep number theoretic connection to the equivalence problem of quadratic forms over the integers. But in general, now the proper way to state this is really that you have two lattices that are isomorphic, and you want to find an isomorphism between them. So that led to a version of Falcon, which is just as small, even faster, and much easier to implement. So the supersingular endomorphism problem is the same problem in a different fashion. Is that what we are talking about? Is what this workshop is about, which enables isogeny-based cryptography. Alternating trilinear form problem, that's also UA model that's out of the competition, but still very interesting that you have two forms which are trilinear, which meaning you put in three vectors and the output is a scalar, and it's linear in every variable, and it's alternating because if you put in the same vector twice, you get 0. And it has a natural action of GL and FQ. And kind of the problem is if you're given two forms that are equivalent, find the connecting element in GL and FQ. So these are just some examples, but it really shows you the diverse areas of mathematics that come in play here, and also kind of like a cautionary tale that I mentioned. So again, these are all very promising problems, but the schemes they're based on, they're 2 to 3 years old. So it's definitely a very exciting time if you want to look at interesting mathematical problems that have connections to the real world. I kind of want to make this point often because I often see, I mean, I'm come from Hungary, so I don't know how it is in other countries, but very often if someone interviews a mathematician, the first thing is, okay, it's very good that you do this, but what are the real world applications of that? Yeah, that's when a mathematician just scrolls under the table and I don't care about that, but I have to give an answer. And every single time they just say, yeah, but there is factoring and whatever. And even if they don't do factoring at all, or they don't even do number theory, they say mathematics is very important because credit cards are protected by factoring, which is not true. And I mean, and they don't do number theory; they have no connection to that. But now they can even finally say that this already covers probably 10 different branches of mathematics. So they should be able to find an application of their mathematics in post-quantum crypto. Like the exact person was working in convex geometry, and I told him, why didn't you say lattices, right? And it's much closer to what you do. So indeed, the question is, why are people really working on this still after the standardization? So indeed, it's really a big problem to really see that the new schemes are actually secure. That requires still years and years of actual research to give enough confidence in some of the schemes. Can you make them faster or more compact? So indeed, there's still probably not quite there for especially for isogenies. We're not there for practical deployment. So we have to make them faster or smaller, hopefully not sacrificing security. Otherwise, it would be very easy. Then, indeed, can we really integrate them in actual protocols that we use in the world or IoT devices? So indeed, I mentioned that poses a whole new set of challenges. And that's maybe even a more pressing challenge for certain applications. So at some point, my university was contacted by a company that makes wheels for cars, or steering wheels, so not wheels, steering wheels for cars. And they said they have this like 10-year cycle. So if they implement something, it has to be secure for 10 years. So indeed, and they require, I didn't talk about that, but that requires a lot of other challenges. And then there are advanced applications that you really like. You kind of use silently, but it's not clear that you can make them efficient with current tools. And then finally, one thing which I also like to say, and I'm not sure this is even known by everyone, is so NIST, which is the standardization body. Okay, this is my last slide, except for the whale I have at the end. Is that they made a very hard deadline that after 2035, which is less than 10 years now, from now on they will not support classical cryptography, although this might have been derailed by the regime change in the US, but anyway, they haven't changed their recommendations, so we only have a couple years. Okay, thanks. Yeah, the way like. So, I mean, we're probably very much out of time, but if people have questions, I'm happy to answer them.
Yeah, thank you very much for the talk. And you already said it, but if you have questions.
Yeah.
Is it possible that at some point before 2035, a brand new branch appears in the field, or like one branch dying might happen? I hope not. Sixth branch appearing.
That's a very good question. I think by 20, yeah, that's. I'm not sure I can make a good prediction about that. Branch dying, I could very much see that happening. Although, unfortunately, probably isogenies are the best candidates for that. Or not sure, probably multivariate is the best candidate. No, multivariate is the best candidate for that, and then let's hope not isogenies will not be that one. So codes and lattices, so for the whole branch to die, I would probably, probably that would not happen. But I don't know. A whole new branch to appear, I think that could happen at some point. I'm not sure by 2035, because really a lot of this stuff is kind of fueled by. So there were like very new branches like this alternative nonlinear form stuff that came out of nowhere. But then because the new NIST competition was just about to start, it was completely fine. Of course, now it's more or less broken. Not quite broken, but the current instantiations are not good enough. I think what can induce the creation of a completely new branch are indeed these standardization competitions, because I don't know if then people will take a bigger look at it, will become more mainstream. And indeed, there is, I didn't mention that, but there are other standardization competitions. So there is a Chinese one starting very soon. So I think if someone submits something there and that thing doesn't get broken in 1 or 2 years, I think it could develop a new branch. Although that's always a very risky, probably that's the question. Yes?
I want to ask a question actually. So you had like one slide which you skipped because it was boring. I think it was SHA about
for the
maybe it's like is it, as long as I know, it's already implemented in the classical cryptography. So is it like one of the algorithms which still keeps to be post-quantum, even though it's developed before quantum technologies? Or do you think it might get
No, I mean these. So there is actually 2 different ones. I pushed them into one, but they're actually quite different. So hash-based signatures, they are, I guess, quite old, and they all rely on a very mild assumption, which is that a hash function should be collision resistant. So you should not be able to find 2 elements that map to the same. And that and collision resistance of hash function is basically assumed in many other schemes as well. So indeed, these are very conservative choice. The difficulty is, I think, so for signature, I think the signature size is very big. I think the public key is very small.
Or keeping the state otherwise. Or keeping the state.
Yeah, so there is state. Yeah, I'm definitely not an expert on this. I also try to brush it because of that, but indeed there is a stateless and stateful. So stateless is what you want, but for some applications, the state is kind of like a counter you keep track. But for actual signature applications, you don't want that. So for that, public key is very small, but signature size is very big. So that's bad again it's bad again for applications where there are applications where you might not care about signature size that much. And they are very conservative. So indeed, if all goes to everything gets broken, it's a good alternative. So MPC is a little bit different. So that has emerged quite a bit in the last couple of years. So MPC is a branch of cryptography where a lot of people want to compute something in a way that they all have their input, and they don't want to reveal any information about their input, and they want to compute a function on all of those inputs. And you can turn them into zero-knowledge proofs using this MPC in the head paradigm. And the good thing about that is that basically any NP relation you can actually use there. Now, what is the most difficult one is how to instantiate it in an efficient way. But that basically is also like a very generic principle to build signatures. So maybe that's a little bit incorrect of me of like dismissing it so much, but they're very far from my expertise. So that's why I kind of brushed them aside. But they are very good choices in terms of being very conservative. So that will not likely happen, that these get completely broken. But I think indeed, I think signature size is the problem for all of them. I think public key, they're all small, and then signing is, I think, also a little bit slow for hash-based signatures, but verification, I think, is quite fast. I hope that answers the question. Okay. Yeah, sure.
So if I want to implement some of these protocols in applications, would you suggest me to wait for another 5 years until it settles down, or it's still actually worse on?
So that's a very good question. So I think if it's about signatures, I would wait. That's a personal opinion. Some people are like, no, tomorrow. I don't think. So the only risk you're taking is that there's a quantum computer in the next 5 years, and I think you can live with that risk. So I don't think that will happen. Of course, will there be a quantum computer? Everyone who gives an opinion, if it's an expert, they say, I don't know. They give some elaborate answer, and all the others who give an explicit answer, they have some sort of agenda. If they say, no, there will never be a quantum computer, that comes from people who are running a blockchain based on pairings, and if there was a quantum computer, their whole livelihood would kill. And then the people who will say, oh, there will be a quantum computer next year, they're also running a blockchain, but their blockchain is quantum resistant and no one uses it, and they want people to use it. And those are all not bullshit answers, and people jump on answers. So there recently was a blog post by Scott Aronson that was completely misunderstood, because he said, so I think if you misquote it, you could have imagined that he said there will be a new, so there will be fault-tolerant quantum computers by the next US election. Of course, that could be interpreted that there will never be a new US election. Let's not think about that. The other one being is that in the next 4 years, there would be a quantum computer, and he's a big expert. But then he elaborated on his take, and his take was that there will be a quantum computer that will be able to factor 15 in the next 4 years, which is actually still pretty difficult. So there is a current thing that there was some record that factored 15 or 21, but using some cheating, but actually purely factor 15. So there is still a big jump from 15 to a 2048-bit number. So I think, I personally, because of that, I think the next 5 years is probably out of the question, and I would not implement the scheme that I think it still needs. Several schemes need more scrutiny to be sure. So in the next 5 years, not so much, but indeed by 2035, maybe that will become more cautious by then.
No more questions? Then let's thank Péter again.